Okay, now. Okay. So today we are going to do randomness extractors. We'll see the role of the one-shot entropic quantities for this important purpose of randomness extractor. So randomness extractors are very useful for cryptography, also for computational complexity, and I mean indirectly information theory also. But okay, but their main motivation came from cryptography. So the setting is as follows. There are two parties, Alice and Bob, indicated by this two boxes. So let me write. So this is Alice A, this is Bob B. And eventually Alice and Bob want to share a secret key between them. Okay, so you all know the one-time pad, right? If let's say Alice wants to communicate a message to Bob, or vice versa, Bob wants to communicate a message to Alice, and if they want perfect secrecy, then the simplest and it turns out the best scheme is that if an n-bit message, you XOR it with a random n-bit secret key. So secret key means that only Alice and Bob know this key and nobody else knows it. Okay, and this key is chosen uniformly at random from all the bit strings of length n. So the ultimate aim is to is for Alice and Bob to share a secret key. So let me write down. So ultimate aim.
So is this? I mean, are you going to do a secret key distillation protocol?
Yeah.
Okay.
So ultimate aim is Alice and Bob share a secret key. Now, to start off with, what Alice and Bob have between them is something which is partially secret. So we'll quantify what it means to be partially secret. Okay. So they need something to start off with. So what Alice and Bob share initially, okay, is this, which I'll call X. Okay. So X. So let me say, so they start Alice and Bob share X, okay, which is partially secret from everybody else. So we'll call that but the environment. Okay.
So I have a question. So X is given as input to the problem.
So yeah. So think of the problem as starting off with X. So yeah. So X is given as input, and there are certain properties that X possesses. Okay.
So I can think of X as maybe the salt or something.
The?
I mean, X can be thought of as maybe like some imperfect shared randomness or something like that.
Yeah, yeah. So you are right.
Or maybe the seed of some hash function or something which is supposed to be kept secret.
No, not the seed. So seed will come later. Okay. So Alice and Bob. So think of it as a partially secret key. So that's just it shares X, which is partially secret from the environment. Okay. Yeah. So maybe you think of X as a message, but in this diagram, X is not the message. X is what is called. I'm going to write it here. X is called the raw secret key. Okay. So X is called the raw secret. So the raw tells you that it is not fully secret, it's only partially secret from the environment. Okay, we'll quantify what this means very soon. Okay.
So X is not the key.
X is not the final key.
Okay.
Okay. X is the initial key, which is that's why the word raw is used. It is what they start off with. It is only partially secret from the environment. So the final key will be completely secret from the environment. Okay. So let me tell you how this may come about. So let us say Alice and Bob have met sometime in the past. Okay. And they have exchanged some secrets. Okay. They've decided on a secret. So maybe it's a huge secret key. The secret key is, let us say, contains the dates they first met, the date first Alice sent an email to Bob, the date what they ate for the first dinner together, something like that. Okay, the color of Bob's T-shirt, and so these are all the elements of the raw secret. I'm calling it raw because, okay, I mean, they are random for an outside observer. From some outside party, like the environment, doesn't know what color of T-shirt Bob would have worn on that date long time ago. Okay, that so that's why it is random from the point of view of the environment, and it's also secret. Okay? But I will say it's partial secret for the following reason. The thing is, the raw secret key, okay, is made up of crude things like the date they first met, the time when Alice first sent an email to Bob, the name of the restaurant where they first had the dinner together, okay, the color of Bob's t-shirt. So there is some randomness in all this, but it is not as if the color is uniformly chosen at random from 1,000 possible colors. Okay, so if you think of color of t-shirt, t-shirts have maybe 10 or 20 common colors. So it's not such a random thing, and even if you say those like 10 random colors, not all colors are equally likely. I mean, some colors are more popular than the others. So the quality of randomness or the in this key is not very higher. So more formally, so we are formalizing, the entropy of X is not so high. Okay, X has many bits. Okay, because it has information about the color of the T-shirt, it has information about the time when the first email was sent. So X is made up of a huge number of bits, but the entropy is so if X is made up of n bits, the entropy of X is not n. I mean, it is nowhere close to n.
So
That is one
the
problem
notion.
with it.
So
Yeah.
is the notion of partially secret here that Eve sees a concentrated distribution and not sees a uniform distribution on the keys. Is that what partially secret means?
Yeah, yes, kind of. So we'll formally define it. Okay. Just a second. What is this? Sorry about that. Yeah, several calls keep coming. Okay. So am I audible?
Yeah, I can hear.
Yeah. Okay. So by the phrase raw secret key, so you are right. I mean, the view of X from the point of view of the environment E, okay, is not fully random. So the entropy is not X. So let me formally define what is it. So okay, so this is not going to be the final definition, but this is our first attempt at quantifying what raw secret key means. So it says that the entropy of X given E, okay, so there is some secrecy is greater than let us say greater than K, and usually K is much smaller than it. And I should say, of course, like X is a bit
so one thing is not clear at all here. You have not defined the global distribution. So what is X, what is E?
So now
Yeah, so there's a
everything is
joint
defined, right?
distribution between X and E, is it? PXE?
Yeah.
No, might be 4 parties, I think, right? Alice, Bob, X, E. Should be 4 parties, right?
Well, let us say there's a joint distribution between X and E. Yeah,
Okay.
I mean, there are only 3 parties, Alice, Bob, and the environment, no 4 parties. Alice and Bob share the same X. Okay, there is no doubt about it. It's not as if Alice shares X and Bob shares some X prime which is close to X, nothing like that. Okay? They are guaranteed to share exactly the same X. So Alice and Bob, I can think of it as one random variable X.
Okay, so basically, if I wanted to be super pedantic and said that okay, this is a 3-party tripartite distribution, but I looked at the marginal on just Alice Bob, that would be a diagonal distribution.
Yeah.
Okay.
Yeah.
Got it. Thanks.
Yeah.
And it is raw and partial because the joint distribution of X and E is not uniform and it's not in the product form, right?
Well,
PXE is not PX times PE.
Yeah.
And maybe PX is also not uniform.
Correct. Yeah. So, I mean, all of it is captured. So this is the formalization. Okay, it's not going to the final formalization. We'll see why, but this is very close to the final. So the raw secret key, partially secret from the environment, all of it is compressed into
Shouldn't
this.
it be less than equal to K?
No, no, it might be zero also. Then there is no secrecy. Okay. So I want to show that there is some secrecy, that the entropy of X given E, okay, is greater than K, but so let us say the entropy of X given E is equal to K.
Okay. And the upper bound is log cardinality of X.
Which is N, right? So
Yeah.
if the entropy of X given E were N, this means that X is completely independent of E. In other words, the environment has no information about X, okay? And X is perfectly uniform because, I mean, entropy of X is equal to N, which is the maximum, okay? So that would be the dream case, that X is fully secret from the environment, okay? So it's not enough to say that entropy of X is N, okay? So this definition, for example, entropy of X given E allows that H of X is equal to N. Okay, so maybe I should say that. Note, H of X can be N. Okay, so the entropy of X could be N, but maybe Eve knows X perfect. Okay, that is very bad for us. X is a
Yeah.
completely uniform string, but Eve
This is
knows
a
X.
much stronger condition. This is a much stronger condition.
I mean, this is the right condition for us, that Alice and Bob share something which is partially secret from the environment. Okay, so you have to condition on the environment's knowledge. So that is why it is a conditional entropy. Okay, and conditioning on environment, the amount of randomness which remains in X after conditioning on the knowledge of the environment is at least something. Okay, so there is some secrecy. The extreme would be this is zero. Okay, I mean, in the previous case, if H of X is equal to N, but he knows what X is perfectly, then H of X given is actually zero. So that is bad for us. So you want to say things are not so bad. I mean, there is some partial secrecy, but it is not complete secrecy. That means H of X
Why don't
given E
we
is not E, not.
why don't we formulate this in terms of the mutual information between X and E? That
It'll
would be
come down to
equally valid, right?
it will come down to the
It'll
same
come
thing.
down to HX.
So, I mean, what is important here is that there is, I mean, think of it that way, like the partial secret means that given the knowledge of the environment, there is randomness left in X. Okay, so that is exactly H of X given. Okay. Yeah, so this is our first attempt formalization. Is it clear to everybody why this is a reasonable thing? Okay. Okay. So, I mean, whatever the real world type of example which I gave is supposed to capture that. I mean, Alice and Bob have some information common which they believe is somewhat secret and somewhat random. I mean, it is secret from the others because they don't think the others would know exactly what is the date they first met, the color of Bob's t-shirt and all. But so there is some secrecy, but there cannot be fully confident of the secrecy. So it's only partially secret because maybe Alice told her best friend Monica that, oh, you know, Bob actually wore a striking blue t-shirt during our dinner together. Okay. So some information may have leaked out. I mean, she may not have told about the time the first email was sent, but she may have revealed the color of the t-shirt. So some information may have leaked to the environment. So that's one reason for the partial secrecy. Some, but not all information is leaked. Okay. So that is quantified by H of X given E is larger than K, but usually, I mean, think of it as at around K, and K is much, much smaller than it. So that is where Alice and Bob start up. Okay, so this is one real world type of example. Another example comes, for example, if you do some genuine cryptographic protocol, often the result of that protocol is a raw secret key, which is partially secret from the environment. So this can happen in many ways. So it can happen as a result of some other a larger classical cryptographic protocol going on. It can happen because you are doing some steps of the quantum key distribution protocol. But at the end of all this business, which has already occurred, Alice and Bob share the same string X, and H of X given E is larger than K. That's all we know. And think of it as around k, and k is much, much smaller than. So now from this X, Alice and Bob want to extract a truly secret key. So what will they do? Let me explain. So remember, I mean, Alice has a copy of X, Bob has a copy of X. So actually they will apply a function on X. Okay. So let us say so this is called the extractor function. So they apply the same function f at both ends on X, and what they will get is Z. Okay. Some Z. And now this is the string that they're sharing, and typically, okay, so I should say out here, of course, X is supported on a large number of bits, n bits. Now, I mean, presumably, I mean, like we know there isn't enough entropy left in X, right? I mean, h of X given E is greater than K. Now, what I want is this Z should be completely independent from the environment and should be perfectly uniform. So it's reasonable to believe that the maximum Z that I can get is about K. So anyway, we don't know how close we can come to a dream K. So let's say the output Z is n bits long, and like I should say, like m is less than K. So output length n. Okay. So this will be called extracting m bits from m truly random bits from n partially secret random bits. Okay. And what is the hope? That these n bits that one has extracted will be completely independent of the environment. So I should say hope is h of Z given E is nearly 0. That's what I mean, completely independent environment. And yeah, and it should be like perfectly random m bits. So I should also add that h of Z is near n. Okay. Whatever the output length. So this is the aim of the randomness extraction. And then Alice and Bob can use Z as the secret key for future private communication. So is the setup of the problem clear? Yeah. The aim and the setup. Okay, good. So let's proceed. So
Pranam, can I ask a question? So sort of looking ahead, can I just ask one question? Hello?
yeah. Well, I mean, you can look ahead, but anyway, we are going ahead. Yeah. Sure.
No. So is it so? I mean, suppose I ask this question. Let's say I have some distribution of 0 1 to the n, that is n bit hypercube. Okay, and I just want, there is some distribution on it, and I just want one uniform bit. Okay.
Mm-hmm.
It's not even clear that I can do that, right? It's not obvious.
True. It's not obvious.
Okay.
Yeah. And we'll very soon see that the way I've defined it, you cannot even do that. Okay.
Okay.
Yeah. So we'll have to,
Okay.
I mean, modify our setup a little bit. As I said, I mean, h of X given E is not our final formalization of partially secret from the environment. Okay. So we'll see what are the problems with that.
As in the point is that your distribution, the probabilities in that large distribution might be pathological enough that you are not able to divide the space into two parts, so that they add up to half. That might not be possible in any way.
That might not be possible. Yeah.
Okay.
Yeah. Okay. So let us. Okay. So so as Shayantan looked ahead, and quite correctly so. So first, let us see what are the problems. So like if f is a deterministic function, okay, m cannot even be 1. Okay, so the output length cannot even be 1. So let us see why this is the case. Suppose f is a deterministic function of x. Okay, And so whatever f is, so I mean, one of the two outputs, 0 or 1, will be more likely. Okay, so will occur with probability more than half. So let us say 0 occurs with probability greater than or equal to half. Now I just look at the inverse image of 0 under f. So I'll look at those x's which are mapped by f to 0. And let us consider an extreme case where the environment actually has no information about x. So h of x given E is equal to 0. And the entropy of x is also very high. The entropy of x, okay, is larger than n minus 1. But still, I cannot even extract one bit. I mean, life can be so bad. The reason is, look at the distribution, which is uniform on the inverse image of 0 under f. Okay, so look at those x's which are mapped by f to the output with 0, and take the uniform distribution over that. Okay. So the fraction of these x's is greater than half. If I take the uniform distribution, the entropy will be larger than n minus 1. And I've assumed that the environment knows nothing about the distribution of x. Okay. So I've met both conditions. H of x given E is 0 and h of x is larger than n minus 1. But what will f output on this? Always 0. Right? So if f is deterministic, there will be distributions, okay, of the raw secret key for which the output of f will be a constant. Okay, and these distributions are of all of very high entropy and so on and so on. Okay. So this is the problem. So if f is a deterministic function, you cannot even extract one bit. Is it clear to everybody? So we have to make f into a randomized function. Okay. Now the point is that how do you make it to a randomized function? I mean, what we know a private coin randomized function, but remember, really Alice is applying f on her hand, Bob is applying f on her hand. I mean, they share this x, but they're distributed. I mean, they are far apart in space. Okay, so I mean, they cannot meet together to apply this f. Okay. If they met, they would have exchanged a new secret key. So they have shared this x long time ago. Now they are in different continents. So Alice will apply this f, Bob will apply this f. Okay, and they will be applying it independently in their own computers. So private coins algorithms will not suffice. So the only way out is we have to use public coin algorithms. So what Alice and Bob do is that, okay, now it is time to extract a truly secret key. So they first exchange another uniformly random string. Okay. So this is over.
But this string can be public.
Yeah, I'm explaining that. Yeah, absolutely. So D will be much smaller than n. Okay. So this is called the seed length. Let me explain what it means. So the idea is, when it is time to extract, Alice creates a random string y of length d, and d is much smaller than n. Okay. In fact, it will, let us say d is much smaller than even k also, which is much smaller than n. So d is just a little bit of extra randomness. Okay. So she creates a random string y, which is independent of everything else, which is independent of E, which is independent of the old x. Okay. She creates this by tossing some fresh coins in her lab, and then sends it across a public channel to Bob. So everybody can see it, including this environment, this adversarial environment E, who is sitting there, she can also read. Okay, so this is sent through what is called a public authenticated channel. Okay. So what this means in the crypto jargon, okay, is that everybody can see the contents, but nobody can tamper with it. So Eve cannot tamper with it, but she can see it passing by. Okay, so after a few seconds, Bob also has y. So now I can say that, okay, Alice and Bob had the old x, which was a raw secret key, and then they have y, okay, which is independent of everything else, independent of x, independent of the environment, okay, and is perfectly random. Now, can they use this y for some benefit? Remember, y is very small. I mean, one can say, oh, they have got y, then let them just ignore X and output Y, Z equal to Y. But then the output length M is only D, and that's not what I want. Okay. Remember, I would want N to be close to K, ideally. Okay, and D is much, much smaller than even K. So it will be cheating
No,
to
but there is a much more
output
serious
D.
problem. There's a much more serious problem. Y is public to Eve, which is entirely what we don't
well,
want.
correct, which is entirely absolutely what you don't want. Yeah. So anyway, so what they use Y for is that this function F depends upon both X and Y. Okay. And they apply that. And the output is Z now. Okay. And this. And what I want is the same thing. That now some magic happens and Z is independent of the environment. But remember now the environment, so I should make it even clearer. Okay, so hope. Now the environment also contains a copy of Y. So the hope is H of Z given YE, okay, is nearly 0. Okay, and same H of Z is nearly N. Okay. So I mean, at first sight, you may think that this is not possible. Like, what will a little Y do out here? And remember, I mean, now the environment can also see Y. Like, I mean, the Alice tries to make the job easier for her and Bob, but then she has to let loose Y. But now the environment can see Y. But it turns out that this is possible. Okay, so this is an amazing counterintuitive thing that this is indeed possible with appropriate parameters. And yeah, there's a little bit of it left. So the actual setup will have this Y also, and it will be F of X comma Y. So the environment has only partial information about X, quantified by H of X given E is greater than K. The environment completely knows Y, so Y has actually moved to the environment. But nevertheless, the output of the extractor function will be independent of Y and E. Okay, and the output will be almost uniform on its support. Okay. Now, let us see if this is at all possible. So I would like to say that again, strictly speaking, the way I've set this up, this is also not possible. So what do I mean by that? So consider distribution. Okay. So X given E such that so let me explain. So we're looking at the probability distribution of X conditioned on the random variable E. Okay. So let us say we have conditioned on some little E, and yeah. So now this distribution has this property that there is a particular point x0 where there's a peak. So the probability of x0 condition on Eve's knowledge is half. Okay, but the remaining half probability mass is divided uniformly among the rest of the x's, not equal to x0. So let us say this is something like this happens. Okay. Now the question is, how much can you extract out of it? Okay. So a little bit of thought will tell you that if such a thing happens, then no matter what you do, no matter how big Y you take, whatever function F you take, you cannot even, I mean, you cannot extract more than 1 or 2 bits. So the reason is as follows. Okay. Suppose Fxy, which I'm calling Z, and let us say Z is supported on n bits, right? Supported on, let's say, 3 bits or more, something like that. I want to say that you cannot extract more than 2-3 bits. Suppose, suppose Z is supported on 3 bits or more. And remember,
Entropy doesn't match. Entropy doesn't match
yeah, but let us see
for
what is
this
the problem.
distribution.
Yes, yes. So so I'll finally come to why the conditional entropy is not a good way of quantifying this. Okay. So, but let us see what is the problem having a peak like this. So, okay, suppose that you say no, there is this great extractor function which extracts 3 bits. Okay, and remember these are 3 uniformly random bits, and these 3 bits are completely independent of y and e. Okay, and it's uniformly random numbers. So this means that the probability of the Eve, the environment, guessing the output Z is at most 1/8, right? I mean, if Z looks completely random given Y and E, okay, then and Z is uniformly distributed on 3 bits. That means all that the environment can do is random guessing. Okay, and the environment has no information about Z. And if you want to randomly guess the output of a uniform whatever of a uniform bit string on 3 or more bits, I mean it's at most 1/8. Okay, but here is where the contradiction lies. So the environment Eve knows that there is this x0, and with probability at least half, the raw key is concentrated on x0, right? And the environment also knows what is the seed y. So this y is called the seed. That's the jargon. So it's called a seed. You can kind of feel for obvious reasons. Like, I mean, it's a little bit of extra thing you need. It's like a seed which will grow into a big plant. I mean, the extractor randomness is the plant. Okay. So remember the environment also gets to see the seed y. So what the environment will do is that, okay, I don't care about what other x's arise. I can safely guess that x is equal to x naught. Okay, the raw key, because that happens with probability half. And the environment will be correct with probability half. And then, okay, but it has to guess the output z. So fine, it already knows what y was because it went through a public channel. So it will just evaluate f of x naught comma y. And now it's a deterministic function, and whatever z naught comes out, you will just declare z naught to be the guess. And the environment will be correct with probability. So this contradicts the fact that the environment could only be correct with probability 1/8 or maybe even 1/4. So let me make it 2 bits. So this shows that, I mean, in this case, you cannot even extract 2 bits. So is this argument clear? Yeah, okay. To finally finish, what is the entropy of x given E for this distribution? It is close to n minus 1. Okay. So, yeah, so actually it's not n minus, it is close to n over, sorry. So so I should say that entropy of x given E is greater than n/2. Okay, so there can be distributions which have high conditional entropy. So in that sense, the environment, you'll say the environment knows almost nothing about x. Okay, x was n bits long, but I mean the raw key is not so bad. It has about n over 2 bits of randomness left, even given the knowledge of the environment. But how much can you extract? Not more than 1 bit. Even if you allow seed randomness and so on, still you cannot extract more. So this problem is a genuine problem. There's nothing you can do about it. So what you have to do is we have to change our notion of what it means for the raw key to be partially secret from the environment. So far, so clear? Okay, good. So what we will do is we'll change our notion. So we realize that the conditional entropy is not enough, and the new definition I mean, the new definition that works is now easy to figure out from this pathological example. Right? So the problem was that there was this one X naught which had a very high probability after condition. So you don't want that.
So you need the mean entropy to be small.
Yeah. So what we do is, so what we formalize it is, so correct notion from
So it's just like what we see in the one-shot, right? That entropy or mutual information, whatever. These are average quantities. What you really want here is a smoothed quantity which captures the maximum to be small.
Yeah.
Shouldn't it be H mean epsilon?
I'm coming to that. So, okay. So the correct notion of partial secrecy, I mean, thinking of this example should be that even after conditioning on E, the distribution on X does not have high peaks. Okay. So if you're looking at the largest probability is not so large. In other words, negative log of the largest probability is quite large. Okay. So the negative log of the largest probability is H mean. Okay. So H min X given E is larger than K. So this is how
Pranav,
it's
before
normally
we move on, one basic question. So shouldn't we want H of Z given E to be very close to H of Z instead of 0?
No. H of Z given Y should be 0 because the environment should know nothing about Z.
Ah, right. Okay.
Okay.
Sorry. Yeah.
So that is there. But and we want H of Z to be close to M. Okay. It should be.
Yeah.
I mean, really. I mean, M uniform.
Yeah.
So yeah. So we are coming to the the final notion. But I mean, I'm doing it this way to motivate. So this will actually work H min, but it turns out a slightly weaker thing works. Okay. So to make to make more sense of the weaker
Wait,
thing,
1 second. I'm a little confused now by Aditya's question. So we would want that given condition on Y, the conditional entropy would be large, as in there's a lot of randomness left even after E and Y are made public. And that makes sense because
the Y comes later. So the notion of partial secrecy of the raw key from the environment is just this. I mean, it can only involve X and E.
No, I'm not talking about the mean entropy definition. I'm talking about the hope earlier, that H of Z given Y is approximately 0. That is, shouldn't it be just the other way around? That it should be large, and that makes sense because
no, H of Z given Y should be small.
No, but Pranav, then the mutual information between Z and Y is very large, which you don't want.
Oh, is that right? Oh, okay. Yeah, you're right.
Yeah, that says Z is a function of YE.
Exactly. Aditya is absolutely correct.
Aditya is correct.
In fact, the hope earlier should be the same. Approximate.
Should be the same. It should be approximate.
Yeah.
Yeah, given Y, it should be approximate. Sorry. Okay. Yeah. So this is what we want. Okay. Okay. So now what we will shoot for actually, now the final precise formulation. So even saying that entropy of Z given Y is approximately M is often not strong enough for a purpose. What is the purpose? The purpose is we want to use Z as a truly secret key independent of everything else in data cryptographic protocols. Okay. Now, of course, the ideal thing would be Z is completely uniform, independent of everybody else. So H of Z given Y is exactly equal to M. That would be the ideal thing. So with the ideal thing, of course, everything works out fine. There are no issues. But we are unfortunately not at the ideal case. So that's why I wrote approximate. So now the devil is in that approximation. Now, if the entropy of Z given Y, suppose, now what do you mean by it's approximately M? So maybe it is like you'll say, okay, it is N minus 1 or something like that. But the point is already saying that the entropy is larger than M minus 1 just means that, I mean, you can get entropy M minus 1 by taking a distribution Z, which is concentrated on half the bit strings. Okay, it's uniform on half the bit strings. And that's it. So the entropy will already hit n-1, but this distribution, uniform on half the bit strings, is not even close to the distribution which is uniform on all the bit strings. So we want to avoid things like that. And that's why this formalization that the conditional entropy, okay, is approximately n is not a strong enough condition. So protocols which work perfectly, if Z is completely uniform and independent of everything else, they actually may not work well once I say that, okay, entropy of Z given Y is approximately n. Because the distance from the L1 distance of the uniform distribution could actually be quite large. I mean, here the L1 distance is half. Okay. So, so I want to avoid situations like this. So this is what is called composability. So I want the output of this protocol, which is Z, to be used as input to later cryptographic protocols, okay, without any problem. And the later cryptographic protocols can pretend that they're getting a perfectly uniform Z independent of everybody else. Okay, so the analysis can proceed on that assumption. Now, of course, I will not supply such a good Z, but the Z that I supply should still not affect the guarantees of the later protocol. Okay? So for that, this thing is not good enough. Okay? So what we need is we have to strike this out and replace it by the actual hope. Okay?
Why don't we simply use the L1 notion instead of
So
thinking
so
in
that's
terms of
what I'm doing.
entropies?
So the actual
Oh, okay.
distribution, okay. So this is okay. It is closed now. This means it's closed in the L1 notation to what I'll say the uniform on Z, then times whatever is there on Y and D. So it is the marginal on Y. So this is what I want, and this will work for my composability requirement. That the PZYE is the output of the randomness extraction protocol. Okay, so there is a joint distribution. I mean, this process creates a joint distribution between the random variable Z, the seed random variable Y, and the environment random variable E. Okay, and I want this joint distribution to be a close in L1. Okay, epsilon close in L1 to a product probability distribution, namely is perfectly uniform on Z, product, whatever is there. I mean, I don't guess the marginal on Y. So this is the hope that we'll actually work off with, and this is great. So now I can use the output Z without thinking twice in later protocols and tell the later protocols you can pretend that Z is perfectly uniform and independent of everything else. So is it clear? So if I could achieve this mathematical expression, then I'm done for composing. Okay. So after I do this, I can come back to the correct notion of secrecy. So, so this notion of secrecy, saying that the conditional mean entropy is greater than K, it actually suffices for the task of random extraction. It turns out it's a little too strong. Because anyway, what I'm going to output is not the perfect distribution on the right, but something which is epsilon close in L1. So, so it is fine if I don't start off with a random variable X given E with such a large mean entropy, but it's fine if I can perturb X given E to some X prime given E, and that X prime given E has large mean entropy, okay, and X is close to X prime. So in other words, I mean, if I'm doing this perturbation, it is good enough to replace the non-smooth one-shot conditional information or conditional entropy by the smooth version. So it's a slightly weaker requirement. Okay, so what is this telling us? So normally H mean epsilon will be larger than H mean, right? I mean, because there was a maximization involved. So it says that if all I want is a distribution which is epsilon close in L1 to the desired distribution, okay, I can actually I can actually extract that much amount of truly secret key from a raw secret key with less stringent entropic quantities. Okay, so I mean, H mean epsilon is the conditional H mean epsilon is less than the unconditioned version, right? So so a smaller value of K would have sufficed. So that's the idea.
Pranav, I have a question about composability.
Okay.
Hello.
Yeah. Yeah.
So suppose that I feed this Z into another protocol, and that has some epsilon error, and so the errors add up additively, I think.
Yes.
So
by triangle
if
inequality.
by triangle inequality, exactly. Now the point is, if I repeat these protocols a polynomial in n number of times, okay, then my error is epsilon times some poly n. So
Yes.
can my epsilon go down to 1 over poly, as in is it a negligible function?
No. So think of epsilon
Or
as
is
a
it a
small constant.
constant?
Think of epsilon as a small constant. Okay.
Epsilon is a small constant. That means that I cannot compose these protocols a poly number of times, right?
No. So if you want to compose it, then you have to start off with small subconstant epsilon. Okay. And so the formulas will still remain the same. I mean, h min epsilon. Okay, but I mean, you are looking at h min epsilon for really small epsilon. Okay? So that will be probably something close to the unsmoothed h min. Okay, but fine. I mean, that's how life is.
Okay.
Nothing you can do about it. Okay. So, and yeah, and vice versa also. So you can yeah. Okay. So the final requirement is that partial secret from the environment is formalized by h min epsilon of x given E is larger than K. And finally, I hope to get a joint distribution on Z, Y, and E, which is epsilon closed in L1 to the uniform on Z times something on Y. Okay, so these are the final definitions that are final requirements that will work with. Okay. Any questions? Okay, so let's proceed. Yeah. So how do we go about doing it? So let us.
Just a small spoiler. So this is that classical decoupling thing that we had done before the ISIT presentation, right? Something like that.
Something like that, yeah, classical decoupling. So the setup was. So there is X. And now what? So this is what is called a strong extractor against side information in the literature. Okay. So strong here means that. So what is this? What strong requirement? The strong requirement is that this Y is included as part of the environment. That's, I mean, historically, people first define weak extractors where they forgot to include Y in the environment. But here, I mean, we are including Y. That's what it means. Okay. So here is maybe one of the oldest methods of doing randomness extraction. Okay? And as Shantan just said, this is very reminiscent of classical decoupling. Okay? So it uses what is called two universal hashing. I'll explain what this means. So this seed randomness, okay, Y, is thought of as the description, okay, of is thought of as a description of a certain function. Okay, so so this extractor function f, okay, yeah. So I've written f of x comma y. So alternately, I can think of I can think of the same expression in this form.
You can just say that you have a family of functions, and that family is essentially indexed by the y's.
Well, yeah. So let me.
And that's
Yeah,
it.
yeah. So yeah. So let me do it systematically. So I can think of f of x comma y instead as a function with only one input x, the raw key, but this function is indexed by a parameter y. Okay, so it's just another way of writing the same thing. But this will help in our viewpoint. Okay, so for this two universal hashing based extractor, what we need is we first need to assume a mathematical result that there is a family of functions with a certain property, which are called two universal hash functions. So this family of functions is indexed by a short bit string y. Okay. So how many functions are there in this family? There are 2 to the d functions in the family, and each function can now be indexed by bit string y of length d. Okay. And what is the extraction protocol? So of course, X was the raw secret key shared between Alice and Bob. Alice now chooses a random bit string of length d, call it y, sends it to the public authenticated channel. This bit string y is thought of as the name of a function from this family. So that's what I'm calling f subscript y. So this is the name of a function from a certain family. So I pick the yth function from that family and just apply the function on x, okay, and call the output of itself. Okay, so now let me define. So what I have is I'm looking at a family of functions indexed by y. Okay, so this is what I mean. So fy, okay, where y is a bit string of length d. So this family of functions, so there are 2 to the d functions family. So this family of functions is said to be 2 universal. So definition, if and only if so take any 2 bit strings x prime of n bits, okay, different bit strings x not equal x prime. So what I want is probability under the choice of y, okay, that fy x1 equal
Fi
to
xx prime, xx prime. You didn't define x1. You defined
oh,
xx
okay,
prime.
x right.
No, what the probability that they're equal, that there's a collision, that is small. Here, you're not. The event is not a collision. Z and Z prime are different.
Yeah. So I'll relate it to collisions very shortly, but yeah, but this is the definition of two units. So let's parse that. So this family of functions f subscript y, okay, is said to be two universal family. Remember, two universal is a property of a family. Okay, it's not a property of one function. So this is said to be two universal family if for all strings x not equal to x prime, okay, from the domain. So x prime are bit strings of length n, but and take x not equal to x prime. Now I want to ask what is the output of f subscript y on x. Let's say I call it z, and f subscript y on x prime. Let's say I call it z. Now, I ask. Let me take a fixed z comma z prime. So remember, the z and z prime are bit strings of length m now. That is the output length. So take any two z prime. Z could be equal to z prime. Z could be different from z prime. Doesn't matter. This expression should hold. So what I'm saying is that if I choose a random function from the family, okay, and two fixed input points and two fixed output points, okay, the input points have to be different, output points no restriction. So what is the probability that a random function from the family maps the first input point to the first output point and the second input point to the second output? That's the question. Now, if I actually chose functions uniformly at random from the full family is, look at the space of all functions from n bits to n bits. This is a huge function space, right? I mean, the number of functions is 2 to the power m times 2 to the n. You can check. Okay. So these are the number of functions I have from bit strings of length n to bit strings of length n. Okay. Now, suppose I choose a random function from this family. What is the probability that a random function from the full family sends x to z and x prime to z prime? Well, a random function should be completely uniform, should not favor one over the other. So this should be exactly 2 to the minus 2. You can even prove it for them. So, so if this fy were chosen to be a random function, then I would expect that this probability is exactly 2 to the minus 2. So a two universal family is basically any family which mimics the random family, okay, up to level 2. Level 2 means for for any two different domain points and any two range points, what is the probability that a random function from this family sends first domain point to first range point and second domain point to second range point? So this should be exactly the same as in the full family. So this is called a two universal family. And the point here is that, of course, I mean, if I take all functions, it forms a two universal family. But much smaller two universal families are known to exist.
Uh, what do you mean by full family?
Full family, of course, satisfies this. A full family is a two universal family. No question about it. Okay.
Okay. Okay.
So let me say so. Full family of functions from the full family of functions from n bits to m bits, okay, is a two universal family. Full family of functions is a two universal family. Okay, but what is the size of the full family? That's huge. Size of full family. It is 2 to the power m times 2 to the n. So it's actually doubly exponential in n. Okay, that is the size of the full family. Now, I don't want such a full family because remember, this y indexes an arbitrary function from this two universal family. If I take the full family as the two universal family, then y will be m times 2 to the n. Now, to extract m bits, I'm wasting a huge seed. Not even n bits of seed, I'm wasting m times 2 to the n bits of seed, which is ridiculous. So I don't want such a large family, but it turns out that much smaller two universal families exist. Any questions, Bundu? So this we will, I mean, you can easily check it offline. So what we'll prove is that so the theorem is there exists a two universal family of size 2 to the power 2n. Okay, so it's singly exponential and no longer doubly exponential. I'll tell you what this family is, and you can go home and check that it is a two universal family.
So my seed needs to be 2n bits now only.
Yeah, so the seed needs to be only 2n bits. Okay, no longer 2 to the power n times n bits. Just 2n bits. Yeah, so I'll tell you what the family is. So treat the domain space, which is bit string of length n, okay, as a so I will think of the domain space 0, 1 to the power n as a finite field, okay, f of size 2 to the n. So there are finite fields of every prime power size. So surely there are a finite field of size 2 to the power n for any n. Okay. So finite field of size 2, you all know it is just integers modulo 2, like 0 plus 0 is 0, the 0 plus 1 is 1, and 1 plus 1 is 0. Okay. So it turns out there are finite fields of size 4, size 8, and so on in general powers of 2. So treat 0, 1 to the power n as a finite field of size 2. So the mapping that you take from bit strings to elements of the finite field, you can take it arbitrarily. There are no issues about that. And now I have to define what is my two universal family. So the two universal family consists of functions of the following form. What happened? What happened? Okay. Yeah. Sorry about that. Yeah.
Sorry. So before we okay, I finish the. I have a question. Yeah, I mean, I just finished writing, and I know this example anyway. But
yeah, but for the other, so take the two universal family.
Yeah.
As functions. So these are functions which send x. Remember, I can treat x as an element of f. So x maps to
ax plus
b. Okay. So the elements of the, I mean, to describe a function, I need to just describe a and b. So the elements of the function, the family of functions are indexed by a and b, and a and b are arbitrary elements of the finite field. Okay. So whatever. So number of such functions is equal to number of pairs AB. So to take any two elements of the field F and define a function AX plus B. Okay, so that is 2 to the. Yeah, so it turns out that this construction gives a two universal family, and the size of that family is 2 to the 3. Yeah, Shant.
Yeah. So I mean, two universal and all is fine. I mean, this all you're doing the hashing because essentially you want to reduce the number of random bits. Great, fine. As in reduce the size
Seed
of
size.
of the seed.
Of the seed.
Yeah, but essentially at the end of the day, the idea is that if you have a random, completely randomly chosen function from 2 to the n to 2 to the m, then that will sort of decouple the systems x and e, ey and z. Sorry, ey and z. That's the idea, right?
That's right. Yeah.
Okay.
Yeah.
I mean, this whole construction would work with a completely random function.
Yeah.
But,
it works with any two universal family. I'm just giving you a two universal family of smaller size. Okay. Sure.
Right.
But yeah, but when you see the proof, all you will see is the requirement that the family be two universal. Okay.
Yes.
Okay. So now, so what is the protocol? Alice actually, I mean, if I'm using this concrete family, so she thinks of bit strings of length n as elements of the finite field of size 2 to the n. Then for the seed, she chooses the pair A comma B uniformly at random from the finite field and sends it across. Okay? So D becomes 2n out here. Okay? And then like we have to evaluate f subscript y of x. Okay, that means like x will be mapped to ax plus. That's all. So Alice will output ax plus b. Bob will also output ax plus b. So that is my z. And the claim is that this z, okay, as I mean, as an average over the pair a comma b, this z becomes independent of the pair a comma b as well as the environment. Okay, amazing. So is it clear? Yeah, what have I achieved?
It's
Okay.
like,
Yeah, some comment. Okay, so let me write down. So what do you have to show, okay, to prove? So PZYE is close to UZ, the uniform on Z, times PYE. So what does this mean? So in L1, so this means that so this is equal to
everybody here understands LaTeX notation, right? I mean, I know Aditya does, but Hari Krishna is fine with this, right?
Yeah, yeah.
Okay.
and then this is so the uniform distribution of Z is 2 to the minus n.
Anyone ask?
Yeah. And now, so this is equal to, so remember y is independent of everything else. So this is 2 to the power minus e, then sum over so this is nothing but EE, right? Because yeah, because of the way the protocol has was designed, this y is independent of everything else. It's independent of x, is independent of e. So really PYE, this P of y comma e is a product distribution. Probability of y times probability of e. Probability of y is 2 to the power minus 2. Now this is probability f of x comma y. So yeah, so I should say that this is probability under the choice of x that f of x y equal to z So, well, it should be probability, probability X given E, right? I've conditioned on some symbol for the environment. Okay. So condition on that, I look, so that bias is the probability distribution of X. So under that probability distribution, what is the probability that f of X comma Y is equal to Z minus 2 to the power minus. So far, so good. Yeah. So now I'm going to use Cauchy-Schwarz. Oh, just a second. What did I write? Probably. Yeah. Yeah.
Sorry,
Okay.
I missed this step. So PZ given YE, how is that the same as this expression? So
Yeah.
so PZ given Y is the same.
Yeah. Yeah. Probability of Z
Okay,
given Y. Yeah. So okay. So what have I
so
done?
the conditioning on E is there.
Conditioning on E is there. There's a conditioning on Y
And we have
also.
fixed conditioning on
Yeah.
Y that appears in the fixed Y inside the probability event, right?
Yeah. Yeah.
And essentially what you're doing is you're feeding in the X. So conditioned on E, you're feeding in this fixed X.
Yeah.
And your
So
probability is
condition.
over those choice of X's. Right?
Correct.
And then the event is saying that what is the probability that for this fixed Y, fxy equal to this fixed Z. That is what is being
Yeah.
said, right?
Yeah.
Okay.
So now we are going to apply Cauchy-Schwarz. Okay? So wait a minute. Some more work. So I will. So you have to do it a little carefully. So square root p. Okay, so the right now I'm still keeping equality. Square root. I'm just splitting p into square root p times square root p, and then I'm going to have this problem. Okay. So nothing has happened. Just I've split p into square root p times square root p. But now I'm going to apply Cauchy-Schwarz. Okay. So 2 to the power minus d. Then this will be so square root. So what is Cauchy-Schwarz? It says that the dot product of two vectors is less than the product of their L2 norms. So what are the two vectors here? The first vector is the vector. So the vector is indexed by y comma e. So the first vector is the vector whose y comma eth entry contains square root p. The second vector is a vector whose y comma eth entry contains square root p times the quantity in the absolute value. So that's what I've done. Okay, so I replace the dot product by the L2 length. So this is the L2 length of the first vector. Okay, the vector whose ye at entry is square root of p. And now I have to use the L2 length of the second vector whose ye at entry is square root of p times the quantity in the absolute value. And now this will become the same thing, square. And there's overall square. Okay. So far so good. This is the application of Cauchy-Schwarz, and that's.
I did not understand the last step.
You don't. Yeah. So let's look at this. Do you understand up to this step?
Yes.
Okay. So this is a dot product. Okay. So what is Cauchy-Schwarz? Let me write it up here. So Cauchy-Schwarz says that A dot B is less than or equal to, okay, L2 norm of A times L2 norm of B, right? You know this.
Yes.
Yeah. So I'm going to now see A dot B out. So I need two vectors, A and B. So these vectors are indexed by y comma e. So the number of coordinates is the number of coordinates in y, okay, which is some 2 to the d, times the number of coordinates in e for which we have no bound, some huge but finite quantity. Okay. So the first vector A is the vector whose ye at entry is just square root p. In fact, the ye at entry does not depend on y. It just depends upon e. Okay. The second vector has ye at entry equal to square root p times the quantity in the absolute value. Okay. So if you look at the quantity in the absolute value, that depends on both e and y. Like e comes in out here, e comes in out here, and there's y out here. Okay. That's it. So that is my a dot p. Okay. So this expression sum over y is square root p times the absolute value is nothing but a dot b, where a and b are defined accordingly. Is this part clear? No?
Yes.
Yeah. So now I'll apply Cauchy-Schwarz. So 2 to the power minus d is as before. Now I have to take the dot product. I have to take the product of the L2 norm. So I have to take the L2 norm of the first vector A. So what is the L2 norm? It is the square root of the sum of squares, right? So this is the square root, backslash square root, and sum of squares. So remember, the entries of the vector are indexed by y comma e. So it's sum over y comma e, and the y-th entry was square root p. So I square it and just get p out. So the first square root from here to here is the L2 norm of E. Is that clear?
Pranav, shouldn't that be just
Yeah.
2 to the d?
That's
Because
a further
it's-
simplification. I will do that. Yeah, but
Oh, okay. Oh.
I'm just working slowly. Okay, I mean, I don't want to jump steps out here. Yeah, is it clear, Hari? So this is just L2 norm of A, and similarly, this is L2 norm of B, right? So again, the vector is indexed by y comma e. So I have to do the sum. Oh, maybe this is what confused. Sum. Sorry about that. Sum y comma e. So the vector is indexed by y comma e. The y-th entry is given by what we had out here. So I square it, so I get p here, and this absolute value square. Okay, that's it. Okay, is this clear now? Finally.
Yes.
So this is L2 norm of p. So fine. Now I just start simplifying. So this is equal to, as Shanton said, what is sum over ye of p? Now sum over pe will give me 1, and then there is sum over y, but the number of y is 2 to the d. So this whole thing becomes 2 to the d. There is a square root outside. There is a 2 to the minus d. So this whole thing becomes 2 to the minus d by d. Okay. And to continue, so this is the part where we'll have to do a little bit of calculation, not much. So this is sum over y e. Okay, I'm squaring it. Sum over y e p e. Okay. Sum over y p, and now I'm going to square the quantity in the absolute value. Okay, so this will be okay, mod square. So I can forget the mod since I'm squaring it. So I'll just write probability so this square minus okay, twice I'm not going to write the whole thing, this probability, okay, and 2 to the minus m, okay, plus 2 to the minus 2. So I've just written the squared expression. Okay, so far so good, Hari.
Yes.
So this quantity I have to square it out. Yeah, so I've squared it. So this quantity is the square of this. Great. So let's start simplifying it. So let's do the easy things first. So this is 2 to the minus 2n that comes out, and then sum over e. Okay. Yes. Sum over ep will be 1, and then sum over y will be 2 to the d. So what do I get out here? I get then the square root. So this whole thing becomes equal to 2 to the minus m, then plus. So that is the contribution from the very last one. Now let's come down to the middle term out here. So 2 to the minus m comes out, okay? And now, what do I have out here? So remember, okay, so let's say middle term and first. Let's do it slowly. So is it clear? I got a 2 to the minus m from the very last term. So middle term equal to sum. Okay, so actually I'm looking at the square of the middle term because there's the overall square root out here, right? So middle term square. Sorry. The whole thing is square. Sorry, I should. Sorry. Okay. No. Let's do it slowly. But I can. So it's 2 to the power minus d by 2 square root. Okay, and now let's call it first term plus second term or minus second term plus third term. Okay. So these are terms within the square. I've not done anything great. Okay, just notation. So let us see what is the third term. The third term is sum ye pe, okay, 2 to the minus 2, right? So this is 2 to the minus 2m. Then sum over ep is 1, and sum over y will be this. So this is 2 to the d. So this will be 2 to the m plus d. Okay. Is this clear? So this is the easy part. Then second term equal to sum ye pe. There is also 2 to the power minus n. There's also a factor of 2. So 2. And now what do I have? It is this probability. Okay. think I think I've forgotten a summation over Z somewhere out here. Some PYE. There's a sum over Z out here.
In the L1, there's a
In the L1.
sum
Yeah.
with ZY.
Yeah, no, there's a sum over Z. And this, okay. So anyway, so I'll do this part again next time, but you have to put in sum over Z out here everywhere. That is important. And then there's a sum over Z. Okay. And then when you square it, this is E, and then it is sum over Z here, and the square will involve that also. How the hell did we move this? Anyway, I think we'll just do it next time. Maybe I'll just later get out and put it. Yeah. So let's do it next time. So it turns out, yeah, there is a sum over Z here, which will go everywhere. And now when you expand out all these terms, it's basically for the first term where you'll use the two universal property of the family of functions. And the whole thing will simplify out, and you'll see what will enter is actually the Rennie-2 entropy of X given E into the picture. And the Rennie-2 entropy is larger than the, Rennie-2 conditional entropy will be smaller than the min conditional entropy. Okay, and that's what we have.
What I don't see is that, yeah, maybe I need to think about it a little, but two universal, kahan se aa raha hai? Matlab, there is just
No,
one
to evaluate the first term.
to
See,
evaluate
the first term is square, and there is a summation over Z also.
summation. Oh, okay. So then there will be two of acha, got it.
There's summation over Z also.
Yeah, that Z was missing, right? That sum over Z was missing. That's the thing. Okay.
That's there's sum over Z also.
Basically, at the end of the day, all this is just that because of that sum over Z, you get events like fxy equal to Z, fx prime y equal to Z prime, fxy equal to
things
Z
like that. Yeah,
things like that. And that collision probability is precisely what you get to be close to 1 over 2 to the 2m.
Yeah. Well, it's exactly.
It's exactly 1 over 2 to the 2m.
Yeah.
Okay.
So basically, at a high level, what was this analysis doing? It was upper bounding the L1 distance. Okay? We want to bound the L1 distance. So it was upper bounding the L1 distance by a L2 distance. That's what Cauchy-Schwarz was for. So, a slightly clever Cauchy-Schwarz. This square root P was there, but finally it was the L2 norm of a certain vector, which is controlling our bound. Okay. And the moment you have the L2 norm of a vector, then what Shanton is regularly calling the collision probability comes in. See, when you're doing the L2 norm, you have square terms. So that's the first term here is square term. And when you evaluate the square term, so remember there's finally probability somewhere. You will be talking of events like what is the probability that if I choose X not equal to X prime, what is the probability that f of X comma Y is Z as well as f of X prime comma Y is Z? Okay? That is precisely the setting of the definition of the property of the two universal functions. Yeah.
Oh, I have a bit of a off-topic question, which specific to what we have done. So this proof, every step is very reminiscent of the decoupling thing. Right? There's a weighted Cauchy-Schwarz.
Yes.
And so it was like, was it that I've always wondered how did they come up with that proof? So is it like they saw this and ported everything over to quantum, the weighted Cauchy-Schwarz?
Yeah.
No,
Well,
there's a master's thesis also, which does the classical decoupling first, which is essentially what Pranav you have done, exactly the same thing. One more application of this, and then they extend to quantum, I guess.
Yeah. So it's quite possible that So I mean this extractor proof with two universal hash functions. So long time back, this was also shown that it works against quantum side information. Okay, I think Renner
Yeah,
and
Renner's group. Yes, yes,
yeah.
yes.
Renner and somebody, yeah. Renner and
They were the first people who did the decoupling theorem, right? The quantum decoupling theorem.
No, I
no,
think
that would be
Hayden
Patrick
and
Hayden and company.
yeah. After
But,
that, Renner jumped in with cryptographic application.
Yeah. So, but this extractor business was done. So I don't know which came earlier. So maybe this came slightly before decoupling. So I don't know if the decoupling guys were inspired by this proof.
It certainly looks that way because striking parallels in both proofs. The weighted Cauchy sorts.
Yeah.
And,
Weighted
all
Cauchy
sorts of
Schwarz
things.
and weighted Cauchy Schwarz. Yeah, definitely. But yeah, but this proof is very strongly classical still because I am using properties like what is the probability that fxy equal to z
fxy equal to z and fxy equal to z prime. Yeah.
No, not z
you can't
prime.
do that.
Fx prime y equal to z prime. Yeah, some z prime and y will be the same. Y will be the same because y is out of this business. It's only z which is in the square expression. So
yeah.
So when you open up that square, you'll get z and z prime. That's correct. And x prime. Also.
In fact, you have to take the summation over y outside. That's what makes it strong.
Yeah. So so this is very classical, and I don't know if the decoupling guys were inspired, but in hindsight, I mean, this can be converted to quantum by taking the quantum analog of two universal hash functions, which are two designs specifically. Then in fact, the same proof goes.
Yes.
Yeah. So anyway, so I'm doing it because this is all old stuff. But yeah, to see like, I mean, sometimes things are presented in a different light in quantum, but many of the ideas are old. To see that these things already exist and have a different view of things.
So our designs, can they be called as quantum hash functions?
Yeah, you can call them.
You can think of them as quantum hash functions. Okay.
Yeah. I mean, they are a little more. I mean, they are reasonably more complicated to define, but I mean, you can view in hindsight, view them as hash functions. Yeah, I mean, hash functions are there to capture two y's or k y's independence.
K y's independence. Yeah.
So designs are also there in a sense to capture k y's moments. So I mean, you cannot exactly say independence, but it's k y's moments. So
slightly weaker notion.
The related notion. I mean, saying that a set of random variables k y's independent means the first k moments are exactly the same as the uniform distribution. Okay.
But it's not if and only if, right? It's not. It doesn't go backwards.
Yeah, it doesn't go backwards. So yeah. So basically, I mean, you may not have a uniform distribution as the underlying or whatever. Yeah, I mean, a uniform. You may not have a uniform product distribution as the underlying distribution, but still, if you can capture the first k moments, you may be able to get your job done. Here, the point to note is that the uniform distribution on n bits, okay, is a product distribution.
Right.
So even that structure is useful. Okay. Whereas if you are going to designs, you have a notion of uniform distribution, but it's no longer a product distribution. So there is a difference, but still, I mean, I guess one non-trivial insight.
I mean, what you're saying is hard.
I mean, I'm saying hard in n dimensions. Okay, hard on unitary n dimensions. Yeah. Hard on unitaries in n dimensions is not a product distribution on
product distribution. Right.
On smaller
I got that. Yeah, that's exactly. But the hard cross R is not hard on 2D. That's hard on 2.
Yeah. So the point here is that even if you can mimic the first k moments of some distribution like hard, which is not a product distribution, you can still get your job done. So that would be an important point of difference between the classical and the quantum. anyways, don't bother about this discussion, Hari. Yeah, I mean, just stick to this proof and we'll come back and do it cleanly again. Okay, so I mean, this discussion will make maybe some sense a few months down the line. When you do a little bit of quantum. Okay, so we'll stop now. We'll see
Okay.
on Thursday.
Pranab, we are Arun and I are meeting at 3. So today, do you have time, or I'll just record the meeting with him?
Okay, just record the meeting.
Okay. Okay.
Cool. So Sayantan, what time do you want to meet right now or something?
Can we? Can I just like finish lunch because I haven't had
Yeah.
lunch yet? So
Yeah.
so
give
let's
me a
meet
call.
at 3. Yeah, we decide. So let's meet at 3, right?
Okay. If you want to meet earlier, let me know. I can do that also.